different types of loads connected to half-wave rectifier. So first we did with resistive load. We understood its waveforms, particular waveforms, its conduction period. If Vin is greater than 0, diode is forward biased. This is the conduction path for the first positive half cycle. Positive half cycle, why? Because Vin is greater than 0. So that is what we said. And we also have some of the animations to understand in the shorter space of time. I think this will play for a while for all of you so that you understand the half-wave rectifier with our load. Okay, so this is where it is. It's the positive wave. So diode conducts during this phase. This is the load current and this is the output voltage. So this is the thing that's being shown over here, right? So just a quick review. So when the voltage becomes less than 0, input voltage becomes less than 0. I think at that instant, this is not conducting, so current is 0. So is the voltage. So that's as simple as that for resistive load. Okay, so it's just taking a while. Yeah, the voltage becomes negative. So at that instant, this is 0, this is 0. That's all. So I did not play this for a while. So, okay, I think some messages are there. Let me see what people have to say to me. So, your voice is breaking, sir, Kamran says. Now, please try to response me. Okay. Anything, any voice problem, please, anyone, please type in. There is a chat, you can type in that. Okay, fine. Kamran, is it fine? Can you hear me now? Yeah, I think most of you can. I think it's the, yes, okay. Yeah, sometimes the connection is unstable, so please cooperate. So there are some more people joining in. So this is the thing. So I just thought to explain you when it is negative. So it's 0. This is the load current and this is the load voltage. It's 0. So that's what it is. That's for the resistive load. Similarly, I would like to go for, let me go back to this. Okay. And I would like to do it for the other case, which is RL load. Okay. So I just want to discuss about the RL load as well. So the RL load animation, I will show you. So this is the shortest way I can explain you with the animations which are made. So for you specifically, so this is for the RL load I have. So observe this. See, this here there is an RL load. RL load means resistor and inductive load. So here you see it goes till there. And at this instant, even though, here the voltage, input voltage is going to go negative, at that instant also it conducts in the reverse direction up to some time. So the reason is because of the inductor. There is some energy stored in the inductor that will not allow the diode to go in the reverse bias direction. Reverse biased in the sense does not conduct. So it still conducts because of the presence of the inductor. Okay. So that's why it conducts. This is the notch you can see here. After some time, the energy in the inductor is 0. That's why this conduction becomes 0. Okay. This is the fact. So this is for the RL load we have seen yesterday. And now coming back to, I think if anybody till here have any issues, please let me know. Then we have RLE load for today's discussion. I think we just discussed about those two circuits in last class. about the resistive load, half wave single phase rectifiers with resistive load, and half wave single phase rectifiers with resistive and inductive load. We did its analysis, we saw its waveforms, everything, each and everything in detail. And one important thing I taught you yesterday is nothing but about the output waveform Fourier series analysis. For every output waveform, whatever the output waveform you have, so whatever the output waveform you get, for example, just now we said when the input voltage is positive, observe these three waveforms just now in the animation. This is for uh, this is just for your RL load, right? Resistor and inductive load. So this is the input voltage. This is the input voltage which where it is greater than zero, it's positive. So I'm just saying that 0 to pi. And after this, up to some extent, I'm taking one more angle. Instead of 180, I'm taking it as beta. So this beta is called as current extinction angle. What is the meaning of current extinction angle? The point after which the current becomes, load current becomes zero, is known as the current extinction angle, beta. Okay, so observe this input voltage is positive till this pi. Even though it is becoming negative, there is a conduction. You can see the load current still conducts. This is because of the reason of inductor, or the energy stored in the inductor. That energy will not allow the diode to go reverse biased. Okay, that energy will not allow diode to go in reverse direction, means reverse bias, off switch. So as a result, it conducts during this phase, and you can see it is the output voltage that is in the reverse direction, because the charge through the inductor cannot reverse immediately. So that is the reason it still conducts, because of the storage energy, as I said. So that's the thing. And this was the analysis we did it for your RL load. Okay, so this is how the circuit looks like. This is the circuit. So half wave rectifier with RL load. Just now we have seen the animation for that. And now what if the load gets changed? Okay, so if anybody has any doubts till here, what is the key point is nothing but the inductor stores energy in the form of magnetic field. So when this voltage is positive, the diode is conducting, it's forward biased. Even though when this is becoming negative or less than zero, this diode has to go reverse bias. But because of the energy stored in the inductor, the diode will not go in reverse bias mode. It will still conduct. The inductor will make sure that this diode conducts up to the stored energy in the inductor, does not become zero. Okay, up to the energy stored in the inductor does not become zero, the diode will conduct. Okay, so that's very important point in this RL load. So you have to understand this. Then the next thing I'm going forward. Okay, before going forward, I just want you to understand one important aspect. As I said just now, suppose yesterday I just discussed, I know there is no need for me to discuss this again and again. Most of the students have understood this, but still I have a habit, because I just want to make sure all my students understand very well each and everything in detail. That's why I just keep on telling them, observe this expression for RL load, observe this for this circuit. It's nothing but it's just a basic thing. If you have studied your circuit theory or circuit analysis or BW or anything properly, if this diode is a closed switch, this is an AC source, this is R and L, is simply a series RL circuit, nothing but series RL circuit. If you apply its voltage balance equation, total voltage is equals to IR plus LdI by dt. That is nothing but the total voltage is getting distributed as the voltage across the resistor plus voltage across the inductor, because in series voltage gets added up. So the voltage across the resistor is IR and the voltage across the inductor is L into di by dt. That is what we have. But input voltage is its magnitude times sin theta. That's V in or Vm sine theta. Theta is omega t in this case. So just this is the differential equation of first order, and you need to provide the solution of this equation using mathematics. So that is like complementary function plus particular integral. So this equation, this is the differential. So differential of this current. So solution must be provided for this current. So that is with particular integral plus complementary function, we should give this equation. I want you to calculate this and let me know how can I get this equation, this equation solution in terms of this one, right? In terms of this one. So that's the job I want you to do, and let me know if you don't get, let me know. Okay. And about the impedance, you know very well, under root of r square plus xl square. Tan theta is b by a. In this case, it is omega l by r. So phi is tan inverse of so and so. You can see that the current is becoming zero at omega t is equal to beta. If you go back to graph, suppose just now I have shown you, it is the instant at beta. If you see, this is the voltage. Okay. Similarly, we have current. I don't know where is the waveform. Yeah. Similarly, we have current waveform. Just a second. That was an example. Just let me go back. See, these are all conditions that you need to put to get the equations and all. I keep on telling everyone, everything is based on mathematics, and you need to learn how to pull mathematics out of everything. That's very, very important part. That's very, very interesting, and that's very, very important. And I think everybody should know this, like how to pull mathematics out of anything. So that is the secret there for engineers. So same thing. See, this is what I was talking about. So it is beta, the extinction angle. After this point, you will see the current is becoming zero, or at this point also the current is zero. So that's why that equation, that condition has to be substituted over here. If you substitute that in this equation, which we got above, which is this one, which we got above 4.12, if numerically I have to say, then you will get to know that the certain condition you can determine out of it, and you can just plot certain statistics or certain waveform. Is something like, there's no need for this waveform to be drawn, but a lot of analysis you can do. What happens to your angle phi with respect to beta? What is the relation? So you can see it's an exponential rise. So that is what it is. You can do that. That's mathematical. And then next thing is the average value of output current. You know, for every waveform, you can find its average value and you can find its RMS value. Okay. You are very well aware, since you're talking about series RL circuit, right? So it's just AC circuits, study of AC circuits. So when we are saying study of AC circuits, we have average value. We need to find, we need to find its average value. We need to find its RMS value. So average value formula, you know, for one cycle, 0 to beta. Current is 0 to beta. Why? Because it is conducting till beta. I naught of omega t dt, d omega t, I mean. So current means voltage by resistance. Okay. So whatever the voltage is there, voltage we know very well. What is the voltage? See, this thing is calculated with the help of the previous equations. Like, you know, the value of this one over here. You can see I naught of omega t is V in by Z of so and so. So certain conditions are modeled over here. Conditions have been modeled, and that equation has been, we have arrived to that conclusion. Okay. So this is like you need to find out how we got this one. But just remember, current is voltage by resistance. So just make sure after solving that expression, you get this one. And if you pull this resistance over that side, left side, current times resistance, it becomes voltage. So whatever is the remaining value is Vn by 2 pi of so and so, whatever you get. So these equations, you need to practice a bit. You need to model them. Until unless you practice them, you will not get it. So root means square value. It's something like root means squared. You see, this is squared, the same thing over above, but this is in terms of voltage we are finding. So this is in terms of voltage. If you're finding in terms of current, this is current, then current in terms of voltage by impedance or resistance. So that's the thing. So you know very well. So these equations will help you. Then finally, I just want to ask some of the questions I initiate. If anybody is having any questions from the audience, they can ask me. Like, this is the operation that you need to know, the animation part which I have expressed. Otherwise, if you don't have any questions, I will go forward with the next type, which is the uncontrolled half wave rectifier for RLE load. Okay, so I'll take a while. And if anything is there, please, if you don't have mic, you can type in. And I think all have joined or not, I don't know. Rahman is here, Kamran is here. Okay, and I don't know everybody. So just make sure all have joined. It's a very important class, right? I'm putting extra efforts and I just want you to learn. So please make sure you utilize it to the full possible extent. Any doubts? Yeah. Okay. So I will finish it, no problem. I'm planning to finish the whole course in 1 week duration of time, because power electronics needs some practice. Not everybody can teach and not everybody can learn very easily. So it takes some time for you to understand the basics. But some more basics I'm going to discuss today with respect to what do you mean by a flyback capacitor, and what do you mean by a freewheeling diode? Okay, what is its operation? So these are the very important basics that you need to know. Without that, you cannot solve any circuit. So it's something like most of the time you'll be spending on the waveforms, you'll be spending on the circuit operation, you'll be spending on looking at the circuit operation, how to plot the waveforms. Then you'll be at, like, how can you, using the waveforms, how can you write the mathematical expressions? How can you write the mathematical expressions? That is also very, very important. So most of the people don't know why do we go for Fourier series or Fourier transform, like Fourier series analysis of any given waveform. For example, let me share my screen again. Yeah, I think this is the one. Yeah. So in this case, if you observe, whatever the output waveform I have, for example, I can write its Fourier series components. So observe this. I have this waveform. So this is my waveform. For example, let us say some waveform. So I just want the waveform to be expressed or to represent that in Fourier series. So this is the output waveform. Whatever output waveform I got, I need to write that in terms of mathematical expression. So simply if I substitute the values of n at different instants from 1 to infinity, I should get the same plot. I should get the same plot. If I plot against V output versus so and so angle in degrees, so I should be able to trace this waveform. So that mathematical expression, which is computed instead of that graph into a mathematical equation, can be done with the help of Fourier series. So this is very important. There people fail. So you have to practice this, put it down. It has certain coefficients, a naught, an, and bn. So these coefficients had certain formulas. Those formulas with respect to your circuit conditions has to be resubstituted in your output voltage waveform so that it becomes the output voltage equation for the waveform of the circuit. I know it is quite difficult maybe, but you need to practice. There's no other way out. You need to go through this difficult terminology and difficult equations. Once, I'm sure if you sit and practice, you'll get a lot of doubts. I'm sure about it, but I think you should practice it. I've already discussed in the yesterday's class. So I'm not going to go again to this. And those who ever have some doubts in this, after today's session, probably I will clarify that. I thought I will clarify yesterday, but I'll clarify that. So before explaining about the RLE load, I will, since today's session is about the RLE load first. So this is its circuit diagram. First, I'll explain some important points. What are the important points? See, one thing, you should not do any mistake in the circuit. Second thing, you should not do any mistake in circuit diagram and its operation, discussion of its operation. If you're clear about its operation, if you're clear about the circuit, then you should not do any mistake in plotting its graphs, its waveforms. Like, what is the main intention? I keep on telling. What is the main intention? The main intention is nothing but to get output current. To get output current or load current, it is output voltage by impedance as per Ohm's law. So in order to get output current or load current, one should know what is the output voltages or load voltages. divided by impedance of the circuit, which is the load. If you do, automatically you get the output current, load current, nothing but. So all the circuits are designed to understand or get the value of load current or output current. Very simple. So with respect to different elements connected in different ways with different conditions, what is the output voltage across the load? What is the current flowing through the load? And what is its waveform? And what are its mathematical expressions? That's all. Very interesting. So, but one important thing, why we are calling this as uncontrolled diode rectifier? Because this is the switch which is a diode. It is uncontrolled. Its operation of on and off depends upon the value of this voltage applied. Greater than 0, forward bias. Less than 0, reverse bias. Forward bias means on, reverse bias means off. Okay, coming to RLE load. Now what is very important here? This diode will become forward bias only if, this EMF load is less than input voltage. In other words, input voltage is greater than this load EMF, diode is forward biased. Diode is forward biased. Until and unless this is less, this value is less, or in other words, this is greater than this conducts. So there is a conduction going on. The moment this value is more, it will not allow diode to conduct, but there is some energy stored in the inductor that will allow the diode to conduct, even though it is less, even though it is more. Okay, so we'll see that in a while. What I mean is, first point, one important point is RLE load together in series is nothing but is a DC motor. Simply, it's an equivalent circuit of a DC motor. If you have RL with E as an additional source in the load, then it is known as DC motor. DC motor. So indirectly you are saying that you are attaching the rectifier to a DC motor as a load. So this operation is same. This is what it is. So then conditions, let us look at it one by one, step by step. Let's look at it. So what are we saying? We are saying that the presence of EMF influences the turning on of the diode. What is the meaning of that? If V in is greater than E, diode is forward bias and it conducts. Moreover, I told you the presence of inductor plays a very important role. Inductor is something like it stores energy through it. So the presence of inductor will result in diode to remain in the forward bias even though the voltage becomes negative. The actual idea is, if the voltage is becoming negative, the diode should become reverse bias. But it is not happening in this case because of the presence of inductor. That's very important point. That's what I said. So inductor is pulling the diode to remain in the forward bias even though the input voltage is negative. The output voltage and load current waveforms, I told you the main intention. I told you just now. I told you, those who have joined late also, I'm telling again, it's something like, the main intention is to find out the output voltage and the load current. That's it. That's our main aim. Whatever circuit you design in power electronics, the main intention is to find output voltage and load current and express those in terms of the behavior, in terms of waveforms. And seeing those waveforms, write its Fourier analysis to frame its equations. So every circuit you are able to pull out the mathematics out of it and frame one equation. Right. So that's what it is. So now let's move ahead little bit. Everybody have a different way of teaching, different style of teaching. So I don't know whether you have heard about this inductor or not, but this inductor plays a major role. It stores energy in the form of magnetic field. So until the energy of inductor is becoming zero, it will allow the diode to be in forward bias. The moment the energy becomes zero, inductor energy becomes zero, diode becomes reverse bias. As simple as that. Okay. So now some figures to understand, okay, what it is. Let's see what it is. It can be seen that diode does not start conduction as soon as input voltage is positive. The reason, this point is very important point, which is saying some of the important points you have to highlight, you have to remember, and you have to find the reasons behind that. The reason behind that, I'll tell you. See, what he's saying is, it can be seen that diode does not start conduction as soon as input voltage is positive. So what is the meaning of that? Observe this graph. In this graph, observe this load current is not conducting in the beginning itself. If you see between these two lines, if you see between these two lines, the input value of the voltage, it is there, it is there, it is present, but the current is not present. So what that line is indicating, it can be seen that the diode does not start conduction as soon as the input voltage is positive. The reason behind that is, it is due to the presence of EMF in the load. Okay, due to the presence of an additional voltage source in the load, because it's a series circuit, that voltages gets added up and subtracted, whatever you say. Okay, this meeting is gonna end in 10 minutes. So what is the meaning of that? We all have to re-log in again if you logged out automatically after 10 minutes. So don't worry, again you can re-log in after 10 minutes. Still we have time, don't worry. Okay, so the reason behind this is, it can be seen that diode does not start conduction as soon as the voltage is positive. After some time it conducts. Why? Because due to the presence of EMF in the load. Due to the presence of EMF in the load. Okay, so now conditions, mathematical conditions. First we said it is greater than or equal to E. The instant where it is equal, V input voltage is Vm sin theta is equal to E. Instead of theta, I can say omega t, my wish. Instead of saying Vm, I say V in. These are just denotions. So from this value is equal to E. I want to calculate value of t, time instant. T, what is the time instant? By cross multiplication and this that, I get the instant time. And in terms of alpha, suppose if this is like sine alpha, this is the value, this is the angle. Okay, so that's what I'm getting here, alpha, which is known as delay angle. So I'm just calculating, because I just said that diode does not start conduction as soon as the voltage is positive. That means there is some delay. That delay is known as delay angle, and delay angle is calculated like this. Very simple. So all the conditions, concepts, because of the EMF in the load, because of that, even though in the starting input voltage is positive, the diode does not conduct initially, and that delay is known as delay angle. It is computed with the help of this equation, and this is being discussed in the case of RLE load. Right, any problem can be solved. Anything is given in exam, straight away you can solve. So you have knowledge about this. So now moving on forward, if you go one step ahead, okay, so this is for the first case. Now let's move one step ahead. Yeah, I think I will just because there's not much time of relogging back. Okay, fine, I have some time. I think some 9 minutes or 8 minutes left, no worries. So I'll just quickly go through this. So delay angle versus the ratio of EMF value of E by V in, nothing but the EMF to the input voltage. So what is the meaning? You can plot that. I'll come back to the waveforms, don't worry about anything. So the first thing what I have learned in life is not to worry for anything. If you start worrying, you will never learn or you'll never become anything. That's the worst thing, I know. So just make sure that you don't worry about things, and it doesn't mean you don't worry and you don't do anything. The only things can be achieved by a lot of hard work and a lot of struggle and a lot of knowledge, lot of work you have to do. You can't imagine how much support you have to create and how much knowledge you have to keep. People will stop respecting you if you don't have knowledge. Remember that. Your respect comes with your knowledge and education. So it's very important. You become very knowledgeable in whatever you do and become respectful. It's very important. So now the equations. So the graphs, I'll come back to it when I'm discussing it with an animation part. Okay. And but the equations, the circuit equation, simple. In an earlier case, sir, you said V is equal to voltage across the resistor plus voltage across the inductor plus EMF in this case, because it's RLE load, series RLE. So input voltage is divided across the voltage across the EMF plus resistor plus inductor. Fair enough, right? And after that, the current equation, the solution you have to solve like the previous case which I have discussed for RL load, because this is the differential equation of first order, right? D by dt of first order form. So solution, we have some types of differential equations, if you remember, 5 or 6 types. So in that, on the right hand side, if there is a trigonometric function, something is there, if complementary function plus particular integral, how can you find that solution of that differential equation? Like that, some mathematical problems are there. So you need a great level of mathematics also. I will be happy if somebody can share how to, solve these, get this from this step, because each and everything I alone cannot work. I want some hands, those who can work and show me it, and they learn also. It's not like they're doing some free work. It helps them and it helps me. So it will be very easy if you can solve this and let me know how did you got this equation from there. Okay, so that's the very important part. And the thing is, after this, you know how to find the impedance very well. Impedance is simply, in this case, is Z, because I cannot take the EMF as part of the impedance, because EMF is the voltage. So I'm taking the impedance as RL, R square plus XL square, in other words omega L whole square. So sorry. So tan phi is B by A, that's B is omega L by R, and phi is tan inverse of so and so. So I get that. And here he says at current extinction angle beta, the load current is 0. So hence substituting omega t is equal to beta. I'll come back to that. So if you observe this waveform, I said that still there is a positive voltage, even though there is no conduction in the beginning. So you see there is no conduction in the beginning. That is the delay angle alpha. And the moment after the delay angle, it starts conducting for the positive phase. And that is the beta extinction angle, current extinction angle. After this point, the current becomes 0. And this point is 180. This between these two lines, this is beta and this is pi. Okay. So observe that before only it starts, before only, and in the beginning, after some time, in the ending, before ending the total part till 180, it stops its conduction, because the reason is like the presence of your EMF in the load. That's why. Okay, so that is the thing. So you have to understand that. And this output voltage is like, why it is not at 0, it is at 60, some scaling above, is like when there is no conduction of current. Observe this. When there is no conduction of current, at that instant, whatever the voltage across output is there is equal to the load voltage. In other words, input, you cannot say the most important thing is some voltage is available in the load. So that voltage appears as the output voltage when there is no conduction in the current. This point is very important. Like you need to remember. Okay. So this is a behavior of the diode, we know very well. And this reverse behavior and jumping up is a behavior of your inductor. Just now I said, even though after this point, it should not conduct as per the current, but because of the energy stored in the inductor, it conducts in the reverse and comes back to 0. So I think that's very much clear. So I think I will start with the animation part. So then I can substitute those remaining expressions. And the most important thing is the Fourier series was. Everybody should understand average value, RMS value, and Fourier series of the output waveform, output voltage. Simple output current. Current is nothing but voltage by impedance. So what is the output voltage equation divided by impedance is nothing but output current. So that is the thing. And by just looking at that, you have to say all these things on tips. So I'm just going to the animation. I'll see, because the meeting will end in 2 minutes. So I'll just go to the animation part quickly if I can play it. I think I will try. I don't know. Okay, there's no time. Again, I have to log in. Okay, fine. So I'll wait to rejoin again once in 2 minutes, but I'll wait for some doubts. I'll take up some doubts or questions if anybody have anything for 2 minutes, because the remaining time of the meeting is there as just 1 minute nearly. So please ask. Anything is there, please ask me out. Most welcome. See, everything you have to do in an enjoying way. You have to understand. Without understanding, there is no use. You can't you can't get anything. To get something, you have to lose something. Something like that. So basically, one conclusion, inductor stores energy in the form of magnetic field. Even though the input current is zero, it will influence the diode to be still in forward bias until its energy doesn't become zero. So that's the important point we all have. It's a DC load, DC motor. Rehan asks me, sir, where do we find RLE load? RLE is an equivalent of the DC motor. If you take a DC motor and if you simplify it, you'll find the equivalent circuit of your DC motor by ignoring certain parameters closely. You'll find that it is a